Let's get started. So, my name is Sita Shen. I am a product manager at CelerData. And today's topic is around customer-facing analytics, why customer-facing analytics breaks, and how to build it right. Okay, let's get started. So first, agenda. First, we're going to spend some time talking about what is customer-facing analytics and some of its challenges, right? For example, join versus on-the-fly join versus denormalization, data freshness, especially when you have mutable data, and how to not only have good performance, but consistently get good performance, consistently hitting your P99 goals, right? And then we're going to take a look at some of the technology and features and architectures we're building today to achieve these requirements. And then we're going to dive into have a sneak peek into two reference architectures. So the first one, really focus on real time, focus on data freshness. It will help you to get 10-second data freshness, even with mutable data directly on columnar storage without sacrificing your query performance. And the second architecture really focusing on data governance, right? So it will enable you to have a single source of truth on your data lake in open formats such as Apache Iceberg managed Parquet files, right? While still achieving data warehouse-like performance, query performance. And then we're going to take a look at some industry case studies, right? How industry leaders are future-proofing their data architectures and how they're utilizing all of the technologies and features we're gonna talk about today, right? And then I will share a customer-facing analytics white paper we just finished, and it's actually now live on CelerData.com. I'm gonna share the link after the presentation. And also, if you have questions, please ask them in the chat or in the Q&A session, preferably in the Q&A session. We're going to address all of the questions in the end. Okay, now let's get started. So first, customer-facing analytics, requirements and challenges. Right? So customer-facing analytics is basically the process of directly serving your analytics. So basically OLAP queries, group buys, joins, and group buys, directly to your end users, directly serving them to your end users, right? It's normally very, very high stake, right? Because you're directly serving your end users. And typically it is the company's revenue driver, right? So, and this is the way a lot of data-driven companies build their competitive advantage, against their competitors. Some of the example can be, in ad tech, like Google Ads, Pinterest ads, right? And in fraud detection for especially a lot of financial institutions, right? To prevent fraudulent activities. For example, TRM Labs, Coinbase, and external facing dashboards, YouTube Studio. On the right is actually a screenshot of CelerData YouTube channel. Go and subscribe and watch the videos. CelerData's YouTube Studio page, right? You can see the real-time views, the watch hour, right? Number of subscribers, gains, everything there, on the dashboard interactively, right? And something like DoorDash, for a DoorDash restaurant, to see all of the revenues and all of the good data, right? So analytics directly to your end users. And customer-facing analytics is quite challenging, right? And over the years, we work with a lot of users, and here are some of the challenges we see, for customer-facing analytics. So first is the denormalization challenge, right? Your data naturally is relational, but a lot of OLAP solutions, especially a lot of the real-time data warehouses, are not built with a relational data in mind, right? So either they don't really support join queries at all, right? Or they only allow, single node queries, not distributed joins, right? No data shuffling means you can only join small table to small table, like dimension join dimension. Nobody really does that, but dimension join fact, right? If the dimension table is small enough, to fit in the memory of one node, right? But you can't really do big dimension table join the fact table or fact table join fact table. You're going to run into OM issues, right? Or they just make, join so expensive and slow and expensive, they're practically unusable. Or it's just unoptimized performance, right? And join queries needs a very smart, cost-based optimizer. A lot of the solutions are still using a rule-based rule-based optimizer, which make the performance just too slow for any kind of customer-facing scenario, right? And without the ability to do join, users are forced into denormalizing, typically denormalize all of the data, right? But denormalization, yeah, it does solve the performance challenge. Query latency is good because you don't have to do the join. Joins are expensive, right? But it comes at a very, very hefty cost. So first, you have to consider the cost of the actual, the denormalization pipeline, right? Now, if you do that for batch, it's actually not as bad, right? You just manage like 1,000 Spark jobs. Spark is not really that difficult to manage, right? But if you actually want to do real-time analytics, meaning fresh data, right? Data with a freshness of 10 seconds, a minute, or even 3 minutes, right? Now you need to introduce stream processing. You need to introduce incremental processing, right? You have to manage states, and that is very, very challenging to do, right? It requires a lot of like special technique and actual coding to do. And also you run into problem with your schema getting locked in, right? Because every time you update your original table, let's say you have a dimension table and you have a fact table, right? And you do a denormalization between the two, right? You generate a big wide table, number of rows equal to the number of rows in the fact table, right? That's pretty normal, right? Let's say you want to make an update on the dimension table on one of the columns. Not only you have to change that one column, right? But you have to do data backfilling for the entire flattened white table as well, right? A lot of rows, a lot of backfilling, data backfilling pain, right? And now you're stuck in a single view format that is very, very difficult to update later, right? And we actually ran into a really big user that who were building a metrics platform, right? So different metrics for the stakeholders within the companies to use, but because of them denormalizing everything, updating a metric took like more than like hours, even to days, just because of data backfilling for hundreds of terabytes of data, right? And the last pain point is the last cost is storage explosion, right? So you need to duplicate your fields across tables. It really easily inflates your storage. In our experience, for a lot of the user, is 10 times or more at least, right? So even with modern tooling, denormalization is still, by theory, it is still an operational task, right? And it keeps growing as you grow your data volume, you grow new tables, you onboard new customers, right? And this thing gonna grow a lot faster than your revenue is gonna grow. So this is very, very expensive. And the second challenge is mutable data, right? Mutable data meaning the data changes, right? With updates or deletes, call that upserts, right? And doing that for real time is actually pretty difficult, right? And mutable data is everywhere, for blockchain, for fraud detection, for operational metrics, and they're everywhere. And users are expecting up-to-date results, not still data, right? Especially, when you're serving end users, right? But the problem is legacy architectures, legacy systems are not built to handle mutable data, at least in real time, right? So a lot of the real-time data warehouses, either they lack native upsert or delete or update support, or they rely on something that's called merge on read, right? So basically you write into append and deletes, right? And there's a compaction job that actually merge the files in the backend, right? And that actually is so expensive that it normally slow down query performance. For a lot of the merge on read kind of approach, for example, ClickHouse merge tree, if your data freshness go below, let's say 3 minutes, data freshness, 3-minute mini batches, it can actually really make your query performance slow down. And also there are concurrency issues, with mixed read and write workloads, right? And there are really, not that much workaround, right? So, you can either do stream processing and handle all of the upsert deletes upward, and that doesn't really work, right? Or you just don't do real time. You just do batch and sacrifice freshness, for simplicity, and sacrifice freshness because your data warehouse doesn't support mutable data in real time, right? And then last but not least is query resilience, right? Not only your performance needs to be fast on average, it needs to be fast consistently, right? You want to hit those P99 SLAs. So first, customer-facing analytics has like just crazy SLAs, right? It needs low latency, even under peak load, with very high concurrency, with thousands or for a lot of our users, hundreds of thousands of users simultaneously using that one system, right? And there's absolutely no room for error. And also you have very unpredictable queries, from your end user. You don't know when there's gonna be a query spike, right? And on the technical side, it's very, very difficult to achieve too, right? First of all, your workload can change, right? You don't know when the user's gonna have a good day, just send a whole bunch of query and crash the system, right? And also when data change, query planners are really, really fragile because if data change, statistic change, the optimizer, make mistakes, right? And also infrastructure failures. For a lot of the customer facing use cases, the availability requirement is actually higher than EC2 instances. So you need to account for what if, one of my EC2 instances go down. What do I do? How do I maintain the same performance, right? And also, data change translates to, cache misses, right? And index gets outdated, and that slows down performance too. That really hits your P99 query latency, right? When everything fails, you run into, poor user experience, breach SLAs, right? Really high infra costs, and your engineering team, stuck at firefighting instead of actually, building features, building the data product. So what are some of the solutions? So first, I want to introduce StarRocks. StarRocks is a real-time data warehouse and query engine, right? It's a Linux Foundation project, open source on GitHub. You can check it out. And it actually has two ways of deployment. We're gonna use them later on in this slide. So first is like a real-time analytics workload. So StarRocks can be a data warehouse. It has its own storage engine and its own file and table format, its own optimized storage format for real-time analytics, right? It supports sub-second query at scale. It has best-in-class query performance. It supports on-the-fly joins, so you don't have to do denormalization. I'm going to talk about how exactly StarRocks does that later in the slides. And also, the storage engine, the optimized storage engine, supports real-time mutable data directly on your columnar storage without sacrificing query performance, right? And also, it features a storage compute separator architecture, basically meaning all of the data are persisted in a cloud object storage, and the CNs, compute nodes, basically have a copy or multiple copies of the data, cached in the CNs, right, for serving, right, for better performance. And this is really great for scaling. And StarRocks can also be used as a data lakehouse query engine, right? So instead of using StarRocks' own storage engine, you can ditch that and basically connect your data lake to it. Let's say Apache Iceberg, right? And StarRocks can directly read the metadata of your data lake and directly query your Parquet files on top of your object storage, right? So it supports all of the popular table and file formats, Delta Lake, Hudi, Apache Iceberg, right? And it is a newer generation of query engine, for the Lakehouse, right? It delivers data warehouse-like performance on the Lakehouse. I'm going to talk about exactly how we do that later. So first, how to make join run fast enough so you don't need to denormalize. We just talked about denormalization is very, very expensive, right? So first, we want to talk about the compute architecture, distributed compute architecture, right? These three are pretty abstracted representation of a lot of the data warehouses or query engines we have today in the market, right? So first is scatter gather, right? So basically, it's distributed, but but it bottlenecks on the single node, right? So in terms of join, right? So this, think of something like ClickHouse or Druid, Apache Druid, right? So they are able to run join distributedly, but without the ability to do data shuffling, right? So they can only do a bucketed join, basically, bucket your data the same key as the join key, right? So basically, pre-distribute the data, the shape of the join, right? Or you can do a broadcast join, basically to broadcast all of the smaller tables to all of the nodes in your entire cluster, right? So that bottlenecks on the single node, because if the table doesn't fit in the memory of your smallest node, it's not going to work, right? So this is a very, very simple architecture, for lower cardinality aggregations, single table queries, right? But it's really not suitable for join queries, right? And then you have those like stage by stage or stage by stage computation, that's from like MapReduce. This is more like Spark, right? It has data shuffling, but for every shuffle, the shuffle service persists all of the intermediate results to disk, right? So this is not to intentionally slow down query performance, but is to optimize for long-running ETL workloads, right? So if something fails, it doesn't have to like start from all the way from the beginning, right? It can start like halfway, right? So this is for like workloads, that runs for hours or even days, right? One example can be Spark. And then it's MPP, right? So massively parallel processing. So it features data shuffling, supports shuffle join, right? So fact table join fact table, right? So reshuffle the data to all of the nodes and run the join queries on the fly, right? So one key difference is that everything is purely in memory, right? So there is absolutely no wait time between operators to operators, right? So you get, so it's really optimized for low latency join queries and high cardinality aggregation at scale, right? So this is computer architecture. If you want to run low latency like joins on the fly, you want to look for something that's MPP. And then is query planning, right? And cost-based optimizer is just the state of the art in terms of planning, generating the most efficient query plan, for our executor nodes to execute, right? Query planning is very, very important, especially for join queries. If you take join in account, right? The search space of possible ways to execute a query is just enormous, right? The difference between a good query plan and a bad query plan can be thousands or tens of thousands times of difference, right? And cost-based optimizer, basically, instead of based on heuristic rules, it collects statistic of your data in real time, right? And then estimate the cost of each candidate plan and select the best one for you, right? And StarRocks has exactly this, and the cost-based optimizer is customly built and is deeply integrated, with the execution and the storage layer of StarRocks, right? And this is really difficult to get right the first time. Thank God we're open source. We have users to iterate with us, right? It took us like 2 years, like 4 or 5 years ago to get this correct. So this is query planning to run joins efficiently. And then is the actual query execution on a single node, right? The reason why data warehouses or even Apache Iceberg, Parquet files, everything's columnar oriented. The reason is, let's say you run an aggregated query or you run a just analytical query. You always are fetching things by column, right? You're always doing things by batch, right? So orienting your data in a batch way, in a columnar way, is really good, for OLAP scanning, for OLAP query performance, right? And then you have columnar storage that's storing everything in column. You have vectorization that's basically, we say in memory, we also do things in batch in a columnar way, right? And this works really well with SIMD because SIMD says, okay, so for every CPU instruction, instead of just processing one row of data, we're able to process multiple rows of data. So also batch, right? So for OLAP, the more batch you run, the faster things gonna go, right? We implemented this around four years ago, and this yield around 3 to 15 time, performance benefit, performance gain. This with vectorization, right? And this is exactly the reason why we require AVX2, instruction sets to fully, utilize the vectorization performance benefits. So this is efficient query execution with SIMD or C++ with vectorization. So putting this all together, right? What does fast join look like? So this is the SSB benchmark test between StarRocks, ClickHouse, Apache Druid, out of box, right? So SSB originally is actually a multi-table benchmark test. So you see on the right-hand side with multi-table, this is running the original multi-table SSB test, and everything with the flat is actually a variant of the benchmark created by the folks at ClickHouse. Basically, they did a denormalization of all of the SSB tables into a big flat table and only query the flat table, right? So basically, running all of the on-the-fly aggregations, but not all of the on-the-fly joins, right? You can see on the result, StarRocks flat is faster than everything. But the interesting thing here is StarRocks, even with running the joins on the fly, it's faster than Apache Druid not running the join. And it's almost as fast as ClickHouse, running the flat schema, not running the join, right? So basically, you're able to run those joins basically for free, not to worry about blowing up your storage, not worry about, not be able to do schema change, not to worry about all of the complex denormalization pipelines, not to worry about, the crazy data backfill that you have to do, with the denormalization pipeline without much sacrifice on your query latency and concurrency. So here is one example from Demandbase. Demandbase is a account-based, go-to-market platform for B2B enterprises, right? So they were powering their customer-facing workloads directly on ClickHouse, and they were running into problems, right? Because ClickHouse cannot do big table join, right? So they had to denormalize everything. So data became locked, in a single view format because any schema change would trigger a big data backfilling, right? And for them, this resulted in an exact 10 times of wasted storage, right? So 10 times blow. And this is not like object storage. You shrink your one time to like 10%. This is your original data set 10 times. This is very, very expensive, right? And also, they had to suffer the denormalization pipeline, that's being created, destroyed, reconfigured. They added a lot of overhead, right? And also real-time analytics became impractical just because the sheer number of denormalization pipeline they were running, right? To convert all of those into stream processing jobs, just too much of overhead for them to actually implement, right? So the solution is basically they migrated to CelerData, powered by StarRocks, and they greatly reduced the need for denormalization, right? So because there's no more denormalization, right? So they were able to avoid most of the storage and complete bloat of actually, maintaining those denormalization pipelines and flat tables, right? And they greatly simplified their architecture because no more denormalization pipeline. They can actually go real time now because the schema in your data warehouse is the same as the source of the data, right? And also, they're able to update their schema pretty quickly now because there's no more data backfilling to the flat tables because they don't exist anymore, right? So this is Demandbase. And second, I want to talk about how to achieve a real-time mutable data, right? Second-level data freshness for all of your data, including mutable ones. So this is StarRocks implementation. So this is called delete and insert strategy. So basically for every update and delete, right, is parsed into insert and a delete, right? For every update is insert and delete. For every delete, just deletes, right? And so first it's gonna mark the deletion, during data ingestion, and then filter, the mark, the bitmap at query time, right? And we implemented a primary key index that is in memory, right? That basically tell you, okay, for this primary key ID, where exactly is that stored? So this accelerates the mark delete process, right? So all of the mark deletes are done at data ingestion. So there is no more merge operation, no more compaction in the back end. Best possible query performance, right? So the query performance is not affected by this upsert, by this delete and insert process, right? So you're able to get like second level data upserts directly on your columnar storage. And also, this is fraction of the storage required, if you use something that has a row store too, right? And better query performance too, compared to those that has like a row columnar stored together to solve this problem, right? And one example is Airbnb's fraud detection use case, right? So basically, their data scientists use their data platform to detect violations, to reduce potential losses for Airbnb, right? Which required the system to have first real-time capabilities for all of the data, even mutable data, right? Because a lot of Airbnb's data, for example, like statuses and transactions, they're subjected to change, right? It's possible, there's updates that come in, right? And also they have very, very complex query execution because data scientists can basically write anything with joins and with aggregations on the fly, right? So they basically found StarRocks and they were able to implement this project, right? So real-time data ingestion directly streamed from Kafka into StarRocks primary key table. It's a delete and insert table we talked about, right? So that ensured second level data freshness. And then they were able to run complex queries on the fly without denormalization, right? So they maintain, very high query performance, even with very complex joins and aggregations. And it's flexible because there's no pre-computation. The data scientists can basically query anything they want, right? So they were able to timely identify, frauds with fast ingestion and fast query. So next is low latency with SLA, right? One of the big reasons that your latency is broken is because your cache gets invalidated, right? Or your cache just gone for no reason, right? So first, proactive cache warmup is a really good strategy, for those like customer-facing like workloads. The first time it starts, trigger a warmup to pre-populate the cache with frequently accessed data from last time, right? So it eliminates the cold start performance issue, right? And also you can do something like compute replica strategy, and this is for, let's say, if one of your compute nodes EC2 instance fails, not only you lose that node, you lose all of the cache too, right? So that way you have to touch S3, and that is very slow, right? So one of the strategy is you can have the same cache copied in multiple compute nodes, right? So even there's a node failure, you can redirect to the node that's still alive, still keep your SLA in line. And then to prevent one giant query or one giant scan getting rid of invalidating all of your cache, right? We implemented something called segmented LRU, right? It's still a LRU, but it has a protected segment, right? So into an eviction segment and a protected segment, right? So when data is in the protected segment, it's relatively more difficult to get evicted, right? So that way, it makes sure that there's no like one single big query, big scan, a slack star, that invalidates all of the hot data that you have, right? So this is cache reliability. And also, with data lake, to achieve low latency, we did a lot of work, to migrate a lot of the data warehouse features, such as statistic collection, such as global low cardinality dictionary, to the data lake, to Apache Iceberg, to make sure that Apache Iceberg users still get the same kind of low latency when compared to, if you ingest into StarRocks, right? And also a lot more targeted, specific optimizations for data lake tables, such as, we're able to take advantage of primary key and forward key constraints, actually use them to prune tables and columns. Like for Apache Iceberg, right? We have specific optimization to combat Avro files being too expensive to parse, right? And actually do that in parallel instead of using one node to do all of the metadata parsing and fetching, right? So a lot of targeted optimizations on data lakes as well, to have this kind of performance. I'm going to show some benchmark later. And then to ensure query plan stability, when your data change, your query plan is cost-based optimizers are pretty fragile, right? So we have a framework for a machine learning-based, resource estimation, right, to identify those very expensive queries, either to put them in the queue or to fail them fast, so they don't affect other queries. So not one query can destroy your SLA, for all of the other queries, all of the other tenants. So now let's talk about two reference architectures. I have them all more laid out, more deep dived in the white paper I'm going to share later. So first is a real-time reference architecture, right? So basically use StarRocks as a data warehouse. This way you get the best possible data freshness and query performance, right? Then you're able to ingest data directly from your Flink and Kafka, right? And using StarRocks optimized storage engine, either in a share nothing or share data way, right? You can utilize the primary key table, to get 10-second level data freshness with upserts and deletes. So this is the StarRocks internal table, internal storage ingestion pattern, right? So you see here, we have a Flink connector, you have Kafka connector, and you can use Flink to basically read the CDC of your operational database, if that's what you need, right? And directly sync your operational database data to StarRocks, right? And also, you can ingest more in batch, from your external catalogs, right? From your external data lakes, and actually have some of the data that's real-time ingest into StarRocks, and have your historical data in your, let's say, Apache Iceberg, and join the two together, right? And this is really cool. So this is the real-time reference architecture. And the second one I want to talk about is the Lakehouse reference architecture, more focused on data governance first, right? So you're able to keep your single source of truth on your data lake while still getting data warehouse-like performance, right? So let's say here, it's the same thing, right? So instead of using StarRocks' own storage engine, it's using a data lake, let's say Apache Iceberg managed Parquet files sitting on top of AWS S3, right, as your storage engine, right? So this is when you don't really need much real time. You don't really need data freshness that much when your data lake's data freshness is good enough for you, and you want to prioritize single source of truth. You want to prioritize data governance, right? And StarRocks can help you do that, and also give you that kind of the same data warehouse-like performance with all of the optimizations that we did. And this is a benchmark test, TBCDS 1 terabyte. So this is between StarRocks OLAP table. This is our internal optimized storage, share nothing. And basically share nothing is persisting everything in the local disk of your nodes, right? So this is the absolute fastest way of running a query, right? Not even a cache is needed because everything is local. And the second one is OLAP table, so internal table. With the shared data architecture, basically means the data is persisted in S3, but it's still in StarRocks' own optimized format. And StarRocks directly querying Iceberg table, that's pretty self-explanatory. And Trino directly querying Iceberg table, right? First observation is we see a very similar performance between querying internal table, share data, or even share nothing when compared to StarRocks directly querying Iceberg tables. And to compare, something like Trino, people use that a lot for internal reporting, internal dashboarding. StarRocks is around 7 times faster than Trino out of box on Apache Iceberg. Okay, so these are the 2 reference architectures. I have more deep dive of this in the white paper. I even have another architecture focused on the Lakehouse, actually going to give you, in some scenario, even better performance than the internal tables. I'll share the link later. Go and read it. And here are more customer-facing analytics success stories. You can just search the title on Google. They're going to pop up. So first is the Demandbase story, right? So instead of using ClickHouse, denormalization, switch to CelerData, joins on the fly, save 90% of the storage, simplify their pipeline, able to do real-time analytics. And also they were able to consolidate 40 plus ClickHouse cluster into one StarRocks cluster. And second is HerdWatch, enabling customer-facing analytics directly on the Apache Iceberg, right? Going from Athena to StarRocks, latency went from 2 to 5 minutes to basically sub-second, right? And they were able to unify everything on Apache Iceberg, single source of truth, simplified data governance, right? And the last one, not least, is TRM Labs. They went from BigQuery to Apache Iceberg, right? To Apache Iceberg and StarRocks. And they are serving customer-facing analytics, directly serving the end users with very complex joins and aggregations on hundreds of terabytes of data. So go check out these case studies. And finally, I want to introduce CelerData Cloud, right? CelerData Cloud is the cloud version, enterprise cloud version of StarRocks. It features a bring your own cloud architecture. Basically means your data sits in your VPC, and we have a managing service in our VPC that manages your cluster like remotely. Has a pay-as-you-go architecture, has more security and access control policies, more advanced access control policies, such as row column masking, right? For you to go to production a lot easier. Has better connection for a lot of enterprise BI connectors. And also CelerData features, such as multi-warehouse for workload isolation. This is very useful for customer-facing like workload. So make sure that all of your tenants have the appropriate amount of resource to keep their SLA alive, right? And also other quality of life features, such as automatic interest view. And there is a 30-day free trial running. So go to cloud.celerdata.com and check it out. So faster customer-facing analytics. If any of this sounds interesting to you, please join the StarRocks Slack channel. You can go to this link, starrocks.io/Slack, or scan this QR code right here. Okay, so this is everything I have. Do we have any questions? Let me see. Okay, there's some questions in the Q&A. There's some question in the chat. Let me take a look at the chat first. Hey, Sita, your video is blocking a part of your slides. I'm sorry about that. Didn't see it. Maybe this is pre-recorded. No, this is live. What is your command to? Okay, we're talking about that. Oh yeah, we're gonna share the recording later, and also the slide, so you can check out the slide that were blocked by my face. Yeah, so for MongoDB, yeah, you can use. I think the Debizium has a CDC reader for Mongo, right? And Flink uses that. So if you have that, you can directly read off of that and basically sync that into StarRocks. And because we're able to do real-time data upserts and deletes, so syncing like data from operational database, actually a lot of user does that. Could you comment on, oh, thank you, Du, for helping me answer that. Could you comment on how you handle connectors to external source? Connectors to external source. Are you referring to basically the ingestion pattern? Yeah, so we can read from a lot of sources. Flink, Kafka, Flink. We have a Flink connector that read from Flink, and we have a Kafka connect, and we have a routine load. So basically, one is using Kafka's resource, and one is using StarRocks resource, right? To pull the data. And we have a Spark connector that you can use, Spark to write the data files, and we have external catalog. Basically, we're able to directly read external data lakes metadata, right? So be able to read the data. You can basically do a gigantic insert into and batch load a lot of your data lake data into StarRocks for faster query performance. And we have a broker load, for data in S3, and for operational data sources. If it's a CDC to read, you can use Flink to do that. When using, wait, I think I missed some. Okay, so when using Flink to process data, when the job fails, it can produce duplicate events. By using primary key table, you can deal with this, yes. But can you achieve the same thing with Iceberg in real-time setting? Not as real-time, because Iceberg being a table format, it doesn't have anything to do with memory. It's completely vendor agnostic. So everything is based on S3. So by nature, it's just slower, right? But V3 deletion vector is able to speed up, the ingestion or upserts a lot faster compared to V2, and it's a lot easier to use, right? But it's like nowhere near what our primary key table can do in terms of freshness. Just because we are able to use something that's in memory. We have an in-memory index to accelerate this process. But the overall concept is very, very similar between the primary key table and the deletion vector, both in Apache Iceberg and Delta Lake. Oh, that's a lot of questions. Okay, so could you please talk about how ingestion is scaled? Do we have dedicated real-time nodes? Okay, so this is a two-part answer. So first, for StarRocks, ingestions are done by the execution nodes, right? So share nothing is the backend B nodes. Share data is the CN compute nodes, right? But if you are using CelerData, we have a multi-warehouse. So basically, you can start an physically isolated data warehouse, a warehouse, basically a bunch of CN nodes, and have that dedicated to ingestion. So basically, isolate workloads, doesn't affect your query performance. The B nodes we have in the architecture, does it have single leader or all the FEs can take traffic? Yes, it does have a leader node. But you're able to scale, concurrency, like query planning. If you have like high concurrency, you can scale that by adding more follower nodes. So we have users scale that to thousands of QPS with more FE nodes. So yes, but it's able to scale. Query result set cache can be set on specific query digests. StarRocks doesn't even have a result cache. It has a query cache, but that's like an intermediate result cache. So that's basically designed to accelerate your aggregated queries. So it stores like the result of the first local aggregation. So basically, if your query has a aggregate function and the result is smaller than the memory that the query cache uses, you're able to cache that, but can be set on specific queries. That I'm not really sure. That I think is completely automatic. I don't think it can do that. But StarRocks doesn't have like a result cache, like a Snowflake like result cache. How is the update handled? Can you talk about the strategy in detail? It looks like we mark the record as deleted and then insert a new one. It means StarRocks does the merge on read kind of, yes, but the merge is a lot faster because we have a primary key index, right? The index is basically it's a map, right? Left side of the map is the hash of the primary key columns, or the primary key columns, or the primary key itself, right? So we can, and the right side, the map is the location of where exactly that thing is stored, right? So we're able to find each one of the record in O1 and resolve that on the fly. So there is like no merge process. There is merge process, but it's O1. It's very, very fast. So it doesn't, it's not that expensive. So it's not going to block it's not going to affect your query performance that way. Does StarRocks support writing to Iceberg tables? Yes. Do we need any coordination service like Zookeeper to run StarRocks? No. StarRocks only has two kinds of processes. So FE, the metadata management, connecting to external catalogs, and query planning, right? And that is written in Java. And we have CN or B, depends on like share data or share nothing. That's like the execution nodes. That's purely C++, CMD optimized. So yeah, so no, you don't need a Zookeeper or external like metadata service to run StarRocks. How does the coordination happen? So basically we have FE nodes. Actually, they're not storage and compute separated. So there's like a Raft-like protocol that syncs the metadata between all of the FE nodes. Right? It's a very simple but works architecture. Please elaborate on if the type schema of the data model, star schema, data vault, could have a role / impact on the performance of proposed architecture of StarRocks. I'm not familiar with data vault. Yeah, but I can speak on our star schema or Snowflake schema or yes. So it's joins are not free. If you run joins on the fly, comes with a cost. But in our experience, it's way cheaper than if you denormalize everything, right? Just save the money, from the denormalization, buy more StarRocks nodes, and we're designed to scale. So do that, and also only denormalize, for your crazy workloads. That the current concurrency is just way too high. Like denormalization should only be an option. It should never be a default, right? Okay, I'm answering, but the submitted question, the number is still growing. We have two FEs, 4 CNs with 16 vCPUs and 20 gigs of memory. Our data is stored in S3 in Paimon tables. We're ingesting like 140K records second, but the entire StarRocks cluster go down on querying table. How to handle this use case? First of all, just by looking at it, 16 CPUs versus 20 gigs is not that much, because StarRocks runs very, very efficiently on CPU. So normally we recommend at least one vCPU for like 4 gigs of RAM. Sometimes, for some scenario like 8, if you're using some like cache, like something like result cache, right? Yeah, so definitely more memory, but for this exact reason, we need more information. So maybe could you post this question in the community Slack? Join the Slack channel. Slack channel's here. Join the Slack channel. Post this question there. We're gonna take a look. Okay. Why still 7? I answered 9 already. Context. I have a table in. Wait, where did it go? I have a table in external source. I have a replica with StarRocks Async MV to utilize flat JSON feature to make it faster. Yes, that's part. When using JSON extract with async MV, the CPL doesn't. Yeah, that's a very specific question. Could you post that in the Slack too, in the Q&A? I'll have someone take a look, and also we're gonna reach out later. I have all of the list of the question afterward. For high concurrency scenario, for high concurrency system, ad-hoc queries, the StarRocks cache query plans or do full parse every time? I do not think we do, but I'm not 100% sure. I don't know. Like our query team are always working on something crazy, something new. Maybe this is something that they're working on. We're gonna get back to you on this. I'm not 100% sure, but I don't think we cache them. We cache the metadata though, if it's like external. If we run long running queries, how does failure handle? Basically, we have a retry mechanism, and if you have like other queries, we make sure that your long running query, if it's like way too expensive, doesn't affect those. But the architecture of StarRocks is not. We don't store any intermediate results. So if it fails, it goes from the beginning, right? For high concurrency systems, ad-hoc queries. Wait, I think that's the same question. Can StarRocks create Iceberg tables from routine load jobs? Huh? Create Iceberg tables from routine load jobs. Does it do table management optimization? Create Iceberg from routine. Routine load is like reading from, like it's like ingesting into StarRocks from like Kafka. No, it doesn't. Does it do table management? Today it doesn't, but I'm not sure in the future. Stay tuned. For high concurrency system, ad hoc queries. Wait, why is this question back again? Iceberg, any plans to support partition expression? Yes, we do. The next release, I think, a partition transformation. We support that. When you compare benchmark with Trino, is there any MV or query rewrite? No. We compare to Trino. If we turn on MV, it's gonna be like 500 times difference. MV is, you do a transformation, you don't do the join or aggregation, right? So all of the data are run on the fly. So all of the queries are against the same data set, and everything is run on the fly. So the answer is no, we don't use MV for benchmarking against Trino. That would be pretty bad. As follow up, if I replace Trino with StarRocks, can I reduce my compute by 7 times? That really depends on your scenario. So part of the reason why this performance difference. So I'm gonna say like from the biggest impact to the smallest impact. Okay, 3 impacts. So first is the C++ difference, right? So we're able to implement CMD a lot easier than Trino, right? And then that yields like 3-4 times the difference, 3 times the difference, right? And then it's a cache difference. Trino doesn't have a cache. So for the CMD one, the more complex your query is, the bigger the gap is going to be for CMD, right? And the second one is for cache, right? So basically for this is the simpler your query is, if it bottlenecks on the scan, right? It's gonna yield more performance benefits of using StarRocks because it has a built-in cache for metadata and data cache, mainly data cache, right? And the third reason is basically kind of universal. We do have a lot more crazy statistic that we collect from your Iceberg tables. And a lot of them are inspired and migrated from our internal table, which we, basically collect statistics of our internal data. We migrate a lot of that into Iceberg. So that's like the third biggest difference. But the actual percentage of resource actually need, it completely depend on your scenario. right? It could be the lower on the lower end, for very simple queries. It's probably like 2 times. For like very very complex query, the most I've seen like 20 times. So it really depends on your scenario and query profile. I'm also curious to understand how the compute savings are coming from. Trino has C++ workers, and wondering if we have any benchmark with that. Are you talking about the Velox project or whatever that's called? No, unfortunately, we haven't tested that, but we do have a comparison with Trino up there now. So you can basically compare and see. Presto also cache on local SSD using Alluxio. Yes, that's correct. So I'm trying to compare this product with StarRocks. Yeah, so that is an external cache, right? It's something you need to manage yourself and also come with, the networking costs. And there's also, things that you can only cache, it's one system, right? But we don't really have any publicly available benchmark that compare the two. So, and also like benchmarks are they work to some extent, but you have to test it with yourself at scale, using your own query pattern and your data distribution to get the most accurate result. So I cannot really give any insights here. We have to test ourselves. Okay. I think time series data, not single value. My impression was that deletion vector were only supported in the unreleased Iceberg 3. Yeah, so table spec 3, I think deletion vector just got released like a month ago, I think. But I have to double check. I don't follow the Iceberg thing close enough. Okay, so this is all of the questions. Thank you guys for staying. Thank you. Appreciate that. If there's any more question, please send them in Slack or DM me or send me an email, reach out on LinkedIn, any way that works. Also, please join the StarRocks Slack channel for more fun. Okay, this is everything I have for today. Thank you guys for joining. Thank you so much. Thank you so much for the questions. Thank you. Thank you for showing up. See you guys again next time. Thank you. Bye. Have a great day.